Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to continue the discussion on stereochemistry, which is in chapter 25. Chapter 5 of your book. When we left on Thursday, we started the definition of stereochemistry, and then we gave you some table on the different types of isomers, and then we defined chirality centers and enantiomers. So today we are going to continue with the rest of the study of stereochemistry, discussing diastereomers, Meso compounds, resolution of racemic mixtures, optical activity, and then finally we shall discuss the stereochemistry of organic chemical reactions. But before we go to the discussion of today's session, I do want to let you know that tomorrow, that is Wednesday, September 26th, there will be another online review session. I will send you a reminder on that session tomorrow afternoon. We are going to use the end of chapter questions in chapter 5 of our for that session. I will send you the link tomorrow. And also for those of you who have not picked up your exam, the last exam that we took, make sure you pick them up before we leave today. Okay, of course, we also want to go over the quiz questions that you guys have just taken. Do you want to do that? Okay, so let us go over the quiz question before we begin the discussion of the rest of these topics on stereochemistry. Okay, Maya, can you go ahead and read it for us?
Number one, how many diastereomers are present in the following molecules? A, use L-22 diastereomers in above molecules. B, what is or are the hybridization of the diastereomers carbon or carbons in above molecules?
Okay, very good. And thank you. So the question here is, how many chirality centers, sometimes referred to as stereogenic centers, are present in the following molecules? Okay, how many chirality centers are present here? Let us label this. Let's say this is carbon 1. Let us say this is 1, 2, 3, 4, 5. Okay, which are the chirality centers here? Is 1 a chirality center? No, why? Exactly. So this is not a chirality center. 1 is not a chirality center. That is good. About 2. 2? Why not? What is the definition of a chirality center? It is any carbon atom or any center that is attached to 4 different atoms or 4 different groups, right? Okay? In this case, no, this carbon is different from this carbon. Okay, so in this case, you have this carbon number 2 is attached to this carbon, right, which is attached to an hydroxy group. So that makes it different from this carbon. Okay, so therefore, this carbon here, carbon number 2, is a chirality center because it is attached to 4 different groups, or in this case, maybe 4 different atoms. Okay, the groups are hydrogen, hydroxy. This group right here, carbon attached to hydroxy here, which is in turn attached to 2 other hydrogen atoms, and then also this carbon here. So carbon number 2 is a chirality center. About carbon number 3. Okay, that is also a chirality center. Very good. About carbon number 4. Okay, also a chirality center. Okay, so in this molecule we have 3 chirality centers. Okay, and then of course using arrows point to the chirality center. So that is what we have just done. So let us do that again. So the chirality centers are this here, and this here. How do I know? A chirality center is any carbon atom that is attached to 4 different groups, or it could be 4 different atoms. Okay. Okay. Okay, now, so these are the 3 chirality centers. Okay, now we now ask you, what is the hybridization of each of the chirality centers? What is it? sp3. The point to be made here, this is sp3. The point to be made here, anytime you are discussing or talking about chirality centers, that carbon or that atom must be an sp3 hybridized atom. Okay, keep that in mind. Yes.
Going back to question number 1, why wouldn't the first one be?
This here? That's because it is attached to 2 hydrogen atoms. This carbon is attached to 2 hydrogen atoms. Okay, so that is not the chirality center. This is not the chirality center. 4 different groups, or 4 different atoms. Okay, it could be 4 different groups, or it could be 4 different atoms. Okay, very good. So I think that is clear at this point. It is very important that that is the least you can know about stereochemistry, knowing the chirality center. That is the beginning of knowing stereochemistry. Okay. Ryan, read this out, number 2 first.
Determine the absolute configuration of the chirality center in each of the following molecules.
Okay, determine the absolute. Thank you. Determine the absolute configurations of the chirality centers in each of the following molecules. Okay. Now, was anybody able to do that? What is the? By the way, where is the chirality center here in this molecule? This here? Okay. Is this a chirality center? No, forget it. About this? No, okay. So therefore, we only have 1 chirality center here, and that is this carbon. Now, when you have a problem like this, I want to tell you, your book does it differently than I do. What I advise you to do, take a look, very close look at this molecule. They are giving you the 3-dimensional orientation of all of the groups attached to the chirality center here. In this case, you have, assuming that you are looking directly at this chlorine atom here, this chlorine is coming at you, right? Right? And the bromine is going away from you. What I want you to do, take a look at the chirality carbon and write the chirality carbon and all of the groups attached to it in a Fisher projection formula. That is the first thing you do. Okay? That is the very first thing you do. Okay, how do you do that? What you do, you position yourself so that you could see 2 of the groups or atoms attached to the chirality center in a way that they are coming at you. Do you follow that? Position yourself to look at this molecule in such a way as those two groups will be coming at you. And based on what we know about the stereochemistry of sp3 carbon atom, if two groups are coming at you in an horizontal fashion, what happens to the other groups? They will be going away from you in a vertical fashion, right? So therefore, I will position myself right here. Imagine that I am here. This is me right here. This is my head here. My legs are right here. Okay? So therefore, let me look at this molecule here. This is this molecule. Consider this as the, oh no, not this, that one, this one. See the double bond right here? Based on, from your point of view, this is bromine, right? That is, bromine is blue. Bromine is blue. Chlorine is green, right? This is your double bond, and this is your methyl group. Okay, so this is what I am doing right now. This young lady is looking right here. Okay. In other words, it is for you to position yourself so that you can see two groups coming at you. You could position yourself here, but position yourself in the most convenient way. Do not look for a difficult position. You could position yourself and see the same molecule. So if you do here, if you stay here, what do we have? I'm going to write, focus on the chirality carbon. Okay, so I'm starting right here. So what is on my right? If I am standing, chlorine is on my right. Very good. So chlorine is on my right. So this chirality carbon is here. Chlorine is here on my right. Bromine is on my left. And the carbon-carbon double bond is on top of me. It is very important that you are able to do this. And then the methyl group is below me, right? That is the way you do it. Once you do it that way, everything becomes easy. At this point, then you assign priority to all of those groups attached to the chirality carbon. Okay, so we're going to start. What is priority A? Bromine. Priority B, chlorine. C, what is C? Why the double bond? Okay, very good. Okay, this is the trick. Anytime you have a carbon-carbon double bond, say you have a carbon-carbon double bond, consider that carbon-carbon double bond to be a carbon that is attached to two carbon atoms. Okay, so here, consider this carbon here as being attached to, you have a carbon here attached to this carbon and this other carbon. So this carbon is attached to two carbon. That is the way you look at it. So therefore, it will have priority over this methyl group. You see that? Okay, so this is therefore C. And this is B. So if we want to make our motion, we make our motion from A to B to C. Ignore group D. Okay, well, where would that take us? A to B, we go through B to C. And what is that? That is counterclockwise. So since it is counterclockwise, therefore it is what? It is X. Okay, in this case, it's going to remain X because the group of lowest priority, which is D, is going away from you. So we don't need to make any change. Yes.
Also, you have to look at D being the most priority, or do you look at C?
Which one? Say that again.
Do you look at D being the most priority or C?
No, the
Neglected C really is clockwise, but then do you read, I mean, you neglected D when you looked at it.
yes.
Do you read, evaluate that, to look at the, to see if it's S or R?
Okay, this is what you do. You make a motion from A to B to C. Whatever that motion is, that will determine what the absolute configuration is. Okay? Keep in mind, priority A is highest priority. B is the next, and then of course C is after that. So you go from A to B to C.
Right, but then when you looked at whether or not if you were going to keep it S or R, you looked at priority D.
Well, priority D, the question is priority D going away from you. Right. If it is going away from you, then the motion you get is what you get. What you get is what you get.
Okay, so what if I change the position?
Well, we are not changing the position. We are looking at this molecule.
If I didn't choose that, then I would automatically get it wrong.
If you didn't choose what?
If I didn't choose that orientation of the molecule.
What orientation? The most, no, wait a minute. The most important thing is for you to choose the right orientation. If you get your orientation wrong, then you cannot get it right. How do you get your orientation? Fine. No matter how you look at it, it will be the same. Let us look at it, okay? Wait a minute. Just wait a minute. No, just wait a minute, okay? So at this point, follow me now. Okay, so far the answer to this is S, okay? Okay, so far we agree with that. Now, supposing, instead of this lady looking here, instead of looking at this here, right? Follow me now. Where the bromine is to our left and the chlorine is to our right. Supposing she looks here, you now tell me, I want to now write this. Tell me what the orientation is. I'm going to erase this. No matter how you look at it, you will arrive at the same conclusion. Okay, just a minute. Okay, so this is S. So let us take this out. Just a minute. Okay, based on what this lady is looking at, what is on her right? What is on her right? Bromine, okay. So bromine is on our right. What is on our left? No. You see? What is on our left? The double bond. Very good. Just a minute. What is on top of R? Chlorine, okay. What is below? Metal. Okay, so far so good. Okay, now let us make our assignment. You see, keep in mind that, you see, you are not paying attention, you're busy writing. You asked me this question. Now, keep in mind that you are changing your orientation. This molecule did not change. Okay? So now let us go ahead. Make the priority assignment. What is A? B? C? D? Now let us make our motion from A to B to C. Ignore group D. We now go to A to B to C. So what is that? Counterclockwise. And what is it? Yes. No matter how you look at it, as
The lowest configuration is C is not going away from you, it's going towards you.
why?
And that was my question.
No.
Like, why do you neglect D when you're doing the whole thing and then you just bring back up like, oh.
Bring what back up? Yeah, but what I've done here is to give you, what I've done here is to give you what I'm looking at. Okay, anyway, so at this point, this is S. Okay, everybody agree? This is, no matter how you look at it, no matter how you represent it, as long as you represent it correctly as what you see, it will be the same because the molecule has not changed. If this lady wants, this lady could look from here. Okay, but okay, seriously, supposing this young lady looks from here. No, supposing this young lady looks from here. What is on top of her? The double bond. What is on our left? The chlorine. What is on our right? The methyl. So you have to, once you look, make a correct representation of what you see. Yes.
Maybe you bring the B in because if it's on another plane, then you have to flip the direction. Yeah, and that's like that kind of question. So that's why the space before you when you switch it. Yeah.
What?
So basically you're saying that the CHC was where the BR is when you switch the configuration.
No, I did not switch anything.
No, she's saying if that was the
If that was what?
If the setup was that the D config where D was is where A is, and A is now where D is.
But that's not this molecule. We are, don't make a molecule more difficult than what it is. You see?
That would be hard, right?
Well, okay. Anyway, so this is S. Okay. Now let us go to the next one. So everybody agree this is S. You see how to do it. Keep in mind that you focus on the chirality carbon. Because you have not got into this class of compound. All I want is just the absolute configuration. So in this case, the absolute configuration here is S. Okay. Now, let us look at this molecule here. How many chirality carbon do we have in this molecule? One. Where is it? Right here? Okay. So this is the chirality carbon right here. Okay, very good. So now, before you make your assignment, what do you need to do? Make a Fisher. Very good. Make a Fisher projection. Now, for you to make a Fisher projection, like I say, take a look at this molecule. Look at it in a way that is most convenient for you. Do not make things difficult for yourself. Okay? That is this molecule here. Let me give it to you from your own perspective. Think of this as the carboxyl group. Okay? This is the carboxyl group. This is the other carboxyl group. The two hydrogens. So this is not the chirality carbon. Forget it. This is the only chirality carbon. If you look at this molecule here, based on what this is saying, what is happening to this? This is oxygen. What is it doing to you? It's coming at you, right? It's coming at you. About the hydrogen. Okay, do you see that? Okay. But guess what? If I want to look at this molecule in a way that is convenient for me, do you think I will be looking here? No. In order for me to see two groups coming at me, I won't do that. I will look here. Because now I will position myself here. You see? In other words, if this lady is just doing this, right? Seriously. In other words, position yourself in a very convenient way as long as you see two groups coming at you in an horizontal fashion. That means the other two groups will be going away from you in a what? In vertical fashion. So if you look at this, okay? Okay, so let us now do that. So I'm going to do this here. Let me draw, this is me here. I'm going to assume my head is here somewhere. My legs are here. I'm laying down just like that lady, young lady was laying down, right? Okay. 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 Am I okay? my left hand is here, my right hand is here, right? Okay, now let us now draw a Fisher projection of this carbon. Okay, what is on my right? What is on my right? Don't forget, this lady is laying right here. That's what I'm doing now, right? What is on my right? Exactly, the carboxyl group. So the carboxyl group is on my right. If you are laying, say down there. If I'm laying right here, the way it is right here. The way right here. Okay, this is my nose right here. Right? My head. Okay. I'm not a good artist, you can tell. So now what is on my left? What is on my left? The CH2 attached to the carboxyl group, right? Okay, so that would be this here, CH2 attached to the carboxyl group. Okay? Now, what is on top of me at this point? Hydrogen, exactly. And therefore, what is below me? Hydroxy, right? But the point is, position yourself to look at the chirality carbon such that two groups will be coming at you in a horizontal fashion. As long as you do that, those other two groups will be going away from you in a vertical fashion. Once you do that, make that representation in a Fisher projection. Now, let us now make our assignment. What is A? Priority A? What is priority A? Hydroxy, well, very good. Priority B? What is it? What is priority B? Yes, C double bond oxygen. Because carbon is attached to oxygen here, okay, it's almost as if carbon is attached to 3 oxygen. A double bond is 2, and then you have this here, as opposed to this carbon attached to 2 hydrogen. So this is B. Therefore, what is C? What is C? This group on this side, C. And what is D? Now you make your motion from A to B to C, right? Oh, I'm sorry about that. A to B to C. Ignore group D. And what is that? S. That's a counterclockwise. Therefore, the absolute configuration of this carbon is S. Okay? That is what you have to do. Everybody follow that. Now, if you don't follow this, you should come and see me in my office. Okay, any question before we move on? Okay? Right. Okay, so let's go to the next one. Okay, Spencer, go ahead and read this for us, number 3.
The Fisher projection structure is 2R, 3S, 2 bromo, 3 chlorophene.
Okay, thank you. It said, draw the Fisher projection structure for 2R, 3S, 2 bromo, 3 chloropentane. Now, when you have a problem like this, the first thing, what I would advise you to do, write the structure out in a Fisher projection formula in a vertical fashion. Okay. So in this case, let us forget the stereochemistry. Let us forget the 2R and the 3S. Let's start with 2 bromo, 3 chloropentane. So what is the base name of this molecule? Pentane. Okay. So therefore, I have CH3, and then I'll say 2-bromo, make it a vertical, write it in a vertical position, as opposed to what you guys have been writing in horizontal. Okay, in the 2 position, I say we have, what do we have in 2 position? Bromine. Therefore, hydrogen must be here. Then I say, in the, then we have 3 chloro, right? Okay, let us say chlorine is here. Then hydrogen must be here. And then what is left? CH2, CH, okay? Keep in mind, we do not worry about the stereochemistry of those carbons that are not chirality centers. So in that case, simply just have CH2, CH3. Okay? That is 1, 2, 3, 4, 5. 5 carbon atoms, pentane. 2 bromo, 3 chloro. Now the question is this the right structure? Is this 2R, 3N? That is the question then you ask yourself. If it is not the right structure, then you write the right structure. What to do? We focus on one chirality carbon at a time. You follow that? Well, you may have several chirality carbons in the molecule, but focus on one chirality carbon at a time. So let us number this. Let us say carbon 1, 2, 3, 4, of course 5. Okay, let us focus on carbon number 2, chirality center number 2. What does that look like? What is the absolute configuration? To do that, what do we need to do? In this case, we are already in a Fisher projection, so you don't need to worry about Fisher projection at this time, right? Everybody get this? Okay. So what is, focus on carbon number 2. What is the priority for carbon number 2? Bromine is A. Now, what is B? This group here is B, right? What is C? Methyl, C. What is D? Of course, hydrogen, right? Okay. Now, you want to make your motion. We make our motion from where? From A to B to C, ignore group B, right? Okay, what motion is that? Clockwise. So that is a clockwise motion. Which will be R. However, what is the caveat? The group of lowest priority, D, where is it going? It's coming at you. Exactly. Exactly. Because at this point we are violating the rule. So because the group of lowest priority, D, is coming at you in this Fisher projection, the real absolute configuration will be the opposite of what you get. And therefore it will be S. Okay? Now, what do they want us to do? What they want us to give 2R. So therefore, since we want 2R, what do? We say, okay, that is not correct. Therefore, say bromine is here and hydrogen is here. Do you follow that? So that is 2R. Everybody follow that? Okay, so this carbon now is 2R. Okay? Now, let us go to carbon number 3. We now determine the absolute configuration of that carbon. Okay? So we do the same thing. So at this point, this is R right here, right here. Okay, so let us now go to this carbon here. Assign the priority. Priority A, chlorine. Good. B, which one? Which is B? Keep in mind that this carbon here is attached to bromine, whereas this carbon is only attached to carbon. So therefore, this must take priority. So this group here, therefore, will be priority B, right? And then priority C and D. Okay, now we want to make our motion. What is the motion? A to B to C, ignore group D, right? From here to here, B to C. Okay? Now, ordinarily, that would be what? That should be S, which is counterclockwise, right? That is counterclockwise. Which is supposed to be S. However, what is the caveat here? The group of lowest priority is coming at you, so we have to switch. So therefore, this will actually be R. Okay? Now the question is, what do they want us to write? They want us to do S, right? So actually, what we have here is R, right? What we have here is R. So the thing they want us to write S, so that means the chlorine is here, the hydrogen is here, and now this is S. Which? The numbers, yes, the numbers tells you the chirality carbons. Okay, this here, these two R tells you that carbon number 2 is a chirality carbon, and the absolute configuration is R. This here tells you carbon number 3 is a chirality carbon, and the absolute configuration is S. Okay. Okay, very good. Now, so now we know how to write the absolute configuration. The example we're just giving you here is an example in which you have two chirality carbons in the molecule. Now, supposing I give you this molecule here. If I give you this molecule here with two chirality carbons, and then I ask you, how many configurational isomers do we have from this molecule? How many configurational stereoisomers do we have? Configurational stereoisomers. Now, if you look at this, the answer for this will be what we call, it's going to be 2 to the power of n, where n is the number of chirality centers. N equals to number of chirality centers. Okay. So in this particular instance here, how many stereoisomers do you expect from this molecule here? 4, because n equals to 2, so we expect 4. Supposing I tell you to write all of those stereoisomers. Let us write all of the possible stereoisomers from this molecule. Okay, what will you do? The first thing I will do, I will write the mirror image of this. Which will be this here. That is the mirror image. Let us call this molecule A, molecule B. What is the relationship between molecule A and molecule B? What will you call them? Enantiomers. Will you call the enantiomers? Those molecule A and molecule B, they are enantiomers of each other. In other words, these are mirror images that will not superimpose. Okay? You cannot superimpose them no matter what you do. Okay, now, what other isomer can we get from here? Supposing I move this bromine to the right, right? Supposing I do that. And I keep the chlorine where it is. Okay. Okay, now I have 3 isomers, stereoisomers. What else do I need to do? I then write the mirror image of this. I could write the mirror image of that. Okay, let us call it C, molecule C, and molecule D. What is the relationship between molecule C and molecule D? They are enantiomers. So, A and B and C and D, these are enantiomers. A and B also enantiomers. In other words, they are mirror images that do not superimpose on top of each other. Now, what is the relationship between molecule A and C? A and C. Diastereomer? Yes. Okay. The relationship between A and C is what we call diastereomers. Therefore, what are diastereomers? Okay, is that stereoisomers that are not mirror images, in other words. And these are what we call configurational diastereomers. Okay, another relationship about B and D. How about B and D? What is the relationship between B and D? What is the relationship between them? They are what? Diastereomers. Keep in mind, diastereomers are those stereoisomers that do not superimpose. Diastereomers that are not mirror images. Okay? Stereoisomers that are not mirror images. These are what we call diastereomers. Okay, so the relationship between these also is what we call diastereomers. Okay? Indeed, the diastereomers in this case, the A and C and B and D are what we refer to as configurational diastereomers. Because they are diastereomers as a result of the fact that they do have chirality centers and they are not mirror images. Okay? So now we know what diastereomers are. We also know what configurational diastereomers are. We also know what enantiomers are. Enantiomers, of course, are stereoisomers which are mirror images that do not superimpose. Yes. Yes. We say configurational diastereomers, they are diastereomers as a result of the fact that they have chirality centers. They must have chirality centers. For you to call diastereomers configurational diastereomers, there must be at least 2 chirality centers. Okay? There are some other examples in which you have diastereomers, but they are not configurational diastereomers. We'll show you that before we leave today. Okay, is that clear? Okay. Now supposing I have this. How many chirality centers does this molecule have? 2. Very good. So based on that, how many stereoisomers do you expect this molecule to have? 4. Because 2 into 2 equals to 4. Very good. Now let us write them. Let us write them. Okay? The first thing we do the mirror image first, right? Okay? All right. Okay? So let us call this molecule A and molecule B. So what is the relationship between molecule A and molecule B? Enantiomers. Because they are mirror images that will not superimpose, right? Is that what you're going to tell me? Okay, I will tell you differently in a minute. Okay? There's something slightly different here. Okay, but let's just keep it there. Just hold it. Hold it for now. Now, what are the other isomers, stereoisomers? We move the bromine to the right, to the left, right? Okay, we call this molecule C. And then let us draw the mirror image of that. Let us call this molecule D. Okay? If we take a very close look at molecule A and B, can you superimpose molecule A and B? How will you do that? Exactly. If you turn, keep in mind, when you write a Fisher projection, you could turn the molecule 180 degrees, right? And then slide it on the plane of the paper. The only thing you cannot do is to lift it off the plane of the paper. You cannot do that. But you could turn the molecule. Okay, supposing I hold it my hand here, right? And then this here, and I turn this 180 degrees, and then I slide it into A. What does it look like? Okay. So molecule A and B will superimpose on each other. Even though they are mirror images, they have chirality centers. This type of molecule we refer to as Meso molecule. Let me go and define Meso molecule for you. Meso molecules will be molecules that are two or more chirality centers, two or more chirality centers of carbon and will superimpose on their mirror image and will superimpose on their mirror image. Those type of molecules referred to as Meso molecule. So therefore, the molecule must have at least two chirality centers. It then must be, superimpose on its mirror image. Those are the requirements for a Meso molecule. Okay. So in that case, we go back to here. So in that case, molecule A and B are Meso molecules. So this is a Meso. That is the relationship between them. So what, in essence, what are we saying? Meso molecule are essentially the same molecule. Okay? So therefore, if I ask you, for this particular molecule here, how many stereoisomers are possible? How many stereoisomers are possible? It's no longer, yeah, it's 3. It's no longer 4 because of the existence of Meso molecule within this structure. Okay? So in this case, what is only possible here, the maximum number of isomers that is possible in this case is 3. Of stereoisomers in this case is 3 because these two, molecule A and molecule B, are Meso molecule. Okay, now what is the relationship between molecule A and molecule C? Diastereomers. Those are configurational diastereomers. So therefore, A and B A and C are configurational diastereomers. How about B and D? Oh, the same thing. The same thing for B and D, also configurational diastereomers. Also B and D, configurational diastereomers. So let me define for you again what do we mean by configurational diastereomers. Configurational diastereomers. These are stereoisomers containing two or more chirality centers or chirality carbon that are not mirror images. That are not mirror images. Stereoisomers are. Stereoisomers are. Okay, I'm sorry. Stereoisomers containing two or more. Configurational diastereomers are stereoisomers containing two or more chirality centers that are not mirror images. In other words, these molecules are not mirror images of each other. Those are configurational diastereomers. Okay. Coming back to here. Now, if we now take a look at these four molecules here, molecules A, B, C, and D, we've already said that molecule A and B are the same, right? Because they are meso. Meso compounds are the same. So we therefore say that molecule A is achiral. Achiral means it will superimpose on its mirror image. The same thing we say about molecule B, we also say molecule B is achiral. How about molecule C and D? Well, how will you describe molecule C and D? We say they are chiral. Okay? Molecule C and D, molecule C we say it is chiral. And also molecule D we say also it is chiral. Okay? Now, when we say molecule is chiral, what do we mean? It does not superimpose on its mirror image. That is the absolute condition for chirality. Anytime we talk about a molecule is chiral, the only condition that you could use to test whether a molecule is chiral or not is whether it will superimpose on its mirror image. That is the absolute condition for a molecule being chiral. Is that clear? Yes.
Are you sure? Because it looks like if you turn it, it'll superimpose. For C and D. The way I'm looking at it, I don't want you to get it wrong. I'm a little tired.
C and D?
Yeah, if you turn it 180, wouldn't it the first one?
No.
Oh, no, wait, never mind. I'll be at that one.
Okay. Okay, any question on that? Yes.
Are you saying like, is the whole minute and it's A or you always go up to A or
Say that again.
Is A always the mirror image
Of what?
of the is A always the one that you're going off of?
Well, no, I just made that up. I would have called it C or D, whatever. It doesn't really. See, I guess I'm not getting your question. Okay. Okay. Okay, now, so you begin to now see we have meso molecules, we have diastereomers, configurational diastereomers, we have enantiomers. You need to be able to recognize all of these type of molecules. Very often, you will be given, okay, let us say for example, just as we started, I could give you, I'm going to take a look, for example, I'll take a look at this here, okay? Supposing I write this, carbon hydroxy group, hydrogen on my left, and I say this group here, CH2 with carboxy group right here, and then I also say now it has a carboxy group right here. Okay, supposing I have that. Now, I now come and take a look at this molecule. Okay, the same molecule now, right? I'm looking at it. I say, I do this. Hydrogen is right here because this young lady is right here, right? She's looking right here. Okay? So, I am looking at the hydrogen is on top. The hydroxy is on my left. The CH2 with this is on my right, and the carboxyl is here. Supposing I ask you, are these two molecules the same or not? You will get those kind of questions. Even though I've written that it looks like they are different. The only way you could tell whether they are the same or not is to assign absolute configuration. You cannot just look at it and say they are the same or they are different. I will ask you, what is the relationship between them? If this is R and this is S, and you know that they are stereoisomers, what are you looking for? To make sure they are stereoisomers, they must have the same molecular formula. They must have the same attachment. Once those requirements are met, then the question is, what is the absolute configuration? Supposing I say this is R, after you do your determination, this is R, and this happens to be S. What would be the relationship between them? They are enantiomers, right? In other words, they are not the same molecule. Supposing after you do your determination, you find out that this is R, this is also R. What are you going to say? What is the relationship? What will you say? They are the same molecule. You get those kind of questions. The only way you could determine whether they are the same molecule or whether they are enantiomers or diastereomers is when you assign the absolute configuration. And very often when you also give the names. Okay? So anyway, so at this point you should be able to give absolute configuration to most molecules. But I caution you, you always have to transform the molecule to Fischer projection. But I got one more problem for you before we go. No, not yet. I think we got some more time left. Okay, I will show you what I wanted to show. Maybe you can work on that when you get home. Let us see here. Okay. I didn't know I spent that much time. Okay. Okay. At your own leisure time, okay, I want you to determine the absolute configuration of this carbon here. Okay, you have two chirality centers here, and the absolute configuration of this carbon. Okay. Keep in mind when you do that, focus on each carbon, one carbon at a time. Write the Fischer projection for that carbon and all of the attachments, and the same thing here, and then determine the absolute configuration. Just to give you a clue, You could look at it, this molecule, you could look at it here, or you could look at it here. That depends on you. Okay. So anyway, having said that, I think I will see you guys on Thursday. So for those of you who did not get your exam back, let me give them back to you now.
So could you show us directions for